My name is Rongrong, and I'm gonna give you some background and story about how the two open source community, Presto and Alluxio, work together to bring a faster analytics query engine to users. And I already introduced me a bit. So my name is Rongrong. I'm a Presto Foundation TSC member and committer. I worked on Presto for about 6 years now. And this is my GitHub ID, Rongrong, so you can check out like all I'm working on. So right now I'm working on both Presto and Alluxio. I worked at Yahoo before Facebook, and now I'm at Alluxio, and this is my email. So if you have any questions, follow-ups you want to know, just email me. You can also find me on LinkedIn if that works. Okay, let's get started. So first, let's kind of just go over the two open source projects to give you some background on both. So on Presto, Presto was originally developed at Facebook. It started back in 2012. It was initially kind of developed as an alternative to Hive. Hive was also like started at Facebook as an open source project. But as a like MapReduce framework, it was very popular for analytics, but it's really slow. It's not very suitable for interactive queries. You submit a job to Hive, you wait and you get an email, and then like later you get a notification, that kind of thing, if anybody remembers. So it's the primary goal for Presto is to have interactive alternative. The assumption is like queries typically finish within seconds to minute. And thus, like isolation and reliability might not be the most concerns, like it's kind of assuming that if query fails, you can retry it because it's interactive. It causes a lot of problems later when we try to run ETL queries and then, like try to harden up and stability and reliability and stuff. But that's kind of like when you look at Presto's architecture, you will know this is why it looks what it looks like now. So one powerful thing about Presto is it can use multiple, like you can just implement the connector APIs and can use it to create like any data source, pretty much. So popular query like data sources are like Hive, so Hive connectors, and then there's a GDBC connector, which you can use it to query data from any traditional database, and then you can join separate data sources in Presto, like you can join your Hive data with your MySQL data, for example, without actually need to move in or copy data, which makes it pretty powerful. The workload spans from sub-second to hours. So like if you have like millisecond queries, this is probably not the best architecture to use, but hundreds of milliseconds queries up until 2, 4, 5 hour-ish queries are pretty much the comfortable range for Presto. So it has 17K GitHub stars already and 4K for almost 5K forks. So pretty popular project for open source, and it's deployed at large scale in many of the internet companies. So like if you have a lot of data, it's probably going to be hopefully if it's stable enough for these companies, it will be stable enough for you too. And then some background about Alluxio. It's originally started as a research project in UC Berkeley MP Lab, and it provides a unified namespace across different storage locations. So kind of like mapping from the Presto story of like being able to query data from different sources. This is like kind of being able to manage file systems or your files from different data sources or data locations. And it provides a memory speed data access across network. There's more than 1,200 contributors on GitHub for the project now, so it's also kind of pretty popular in terms of community. It's ranked as 9th most critical Java-based open source project on GitHub by the Google OpenSSF ranking. And it's also deployed in some of the largest companies. So yeah, now let's kind of, we know the background of how the two projects developed separately. Let's see how they kind of like join together and how they meet up together. So first, some background on like Presto's architecture. So I'll kind of tell the story more from a Presto perspective, because this is how, like, I know Presto first, and this is how we meet Alluxio kind of story. So Presto's architecture is mostly designed for disaggregated compute and storage. You can also run Presto directly on HDFS node, so you can have a co-located architecture to run Presto on the HDFS cluster directly. But the common way of using Presto is you have a separate compute cluster. And then the coordinator, when planning the query, would talk to Metastore and talk to the storage for like getting file informations. And then when the work is actually scheduled on the worker, so the actual data processing on the worker would then talk to the storage to fetch the files, get the footer, parse the footer, figure out which columns, you know, like all the ORC and Parquet kind of columnar storage systems. So that's kind of how Presto works. The nice thing about this architecture is it allows storage and compute to scale separately. So like if you just need to store more data, you only need to pay for storage. And if you need to run compute, you can, like when you don't have enough compute, you can add more compute machines or you can spawn new clusters. This made it very cloud friendly. So Athena is based on Presto. You know, it's kind of like fits in very nicely in the cloud like model of things. But then like there's problem with this architecture, right? Like it can potentially have very high latency, especially if your compute and storage are on different locations, right? If you have data stored in S3, but you're running on a private compute cluster, then reading each file, like each IO has very long latency. And even if you are running storage and computing in the same location or in the same data center, it's still not fast enough in a lot of cases for very low latency queries, like if you want sub-second results, right? Like for dashboarding and stuff. And another problem with this is like a very long and very tail latency. Like, you know, when you have to access a different system for your data, you invariably would always have some slow node and slow data, and then like your query basically cannot finish until the slowest data is processed. So with that, Presto actually developed a special connector called Raptor back in 2014, 2015 timeframe. It was kind of an optimization for low latency workload at Facebook. So basically the idea is now let's co-locate storage and compute. So we use, instead of like compute only workers, we actually have workers that has local flash storage, and we would inject the data into the worker. And now in this architecture, you would schedule the compute to be where the data is. And then it's, yeah, so the nice thing is, okay, like now you have a faster data access, but then there's all these problems with the co-located storage and compute, right? You have potentially low cluster utilization because now your cluster size has to scale as the data size scale. And we know that in most cases, hot data is only a small percentage of all your data, but then to store all your not so popular data, you still have to have the storage, and you have to add node, even though you don't need the compute. And unfortunately, interestingly, this actually also doesn't help on tail latency because, again, you know, if your data is only stored on one worker and that worker is stranded for any reason, even if it's a GC or anything, then that processing that split would take longer. And as a result, you pretty much still have a pretty low or like pretty long tail latency in terms of like P99 performance of your query or even P95 performance of queries. It also has some operational side effects, as now instead of only managing the compute cluster, you are managing a storage cluster. You need to manage all the data ingestion pipelines related to, you know, getting the data in and then, you know, facing the data out. And this also kind of leaves a security and privacy issue, especially in the last few years as security and privacy become more and more of a concern. As a warehouse, when we develop a security and privacy strategy, you will have a team working on it, but then you have the special storage that you also need to enforce some security and privacy rules, but then you kind of have to have a special implementation for this. Like how would that gonna work, right? So in 2000, like at the beginning of 2019, we start to ask, can we have the best of both worlds? So basically have a cache-based solution to replace RaptorX. So we get the caching for data in the worker locally, but we don't need to pay for managing for a local storage system and a co-located compute. So you always have the data on remote storage, but then, all the hot data would be in cache. And that's kind of also the time frame when we start to hear, like in a lot of meetups or conferences or events in Bay Area, there will be people asking me, when I go to the events, have you heard about Alluxio? Have you tried Alluxio? It's like, what is Alluxio? Okay. And so, yeah, so Alluxio is it's a standalone service. So it's kind of a managed, it's by itself, it's also a service that runs, you can't have caching run on HDD hard drives, but most of the time you probably have either in-memory or SSD workers on Alluxio clusters as a caching layer. The nice thing about this architecture is Alluxio can work if you have multiple different storage systems or compute clusters or compute engines. If you have Spark, Hive, and Presto, they pretty much operate on the similar set of data. You might potentially have, upstream Spark pipeline producing some data, and then downstream Presto for analytics, consuming the data. And if the data is cached in Alluxio cluster, it's shared among the different storage engine as well, and it hides the latency for the remote storage and hides the complexity of potentially you have data from different sources as well. So yeah, unified namespace and sharing hot data across different clusters. But what if when we only need to use Alluxio to speed up Presto, right? If you only need to run Presto cluster and you have also run a Alluxio cluster, kind of co-located or separate, the nice thing about this is it actually works. It you just set up Presto cluster, set up a Alluxio cluster in the same physical cluster. You can either co-locate the Presto worker and Alluxio worker or not co-locating them. Co-locating them give you slightly better performance, obviously. And it still speeds up dramatically for your workload if your data is in a different network or in a different location. But the downside of this is you're running two clusters, so you have to manage two separate clusters. And when you only need to speed up for one query engine, right? Having two clusters and all the RPC between the two services, there's definitely room for performance improvement. We can definitely get a better performance than this, right? This is definitely not the best performance we can get. So that's when we started to say okay, can we work together to have embedded Alluxio local caching service or a caching solution running inside Presto. So kind of Alluxio as a library inside Presto. So it's a single service. Yeah, that's kind of the architecture we ended up having. So Alluxio developed a library that's we can use as a local caching layer inside Presto. So basically the Presto worker would have SSD managed by Alluxio. And so all the memories are used by Presto for normal query processing, but then the SSD on Presto can be used for Alluxio to manage caching. And Presto still uses the HDFS interface, so it's transparent to the engine. And the Alluxio caching library would optimize for a small page size. So the typical Alluxio cluster setup, right now we have for example, 64 meg block size. This is kind of optimized more for like ETL jobs that would kind of scan files. But Presto as a analytical query engine running on mostly columnar storage systems or columnar file systems like Orc and Parquet. Typically, your analytical queries, you only access a few columns. So the data you read out of each file is kind of like a small chunk all over the place in the file. So like a smaller page size would be better for cache efficiency. And then Presto implements a locality-aware scheduling scheme. So we try to make sure that the same split or the same data is always scheduled on the same Presto worker. Instead of like randomly assigning data to a worker, so data are potentially cached at many different workers. We're trying to always assign the read for the same file to the same worker. So you would have a cache hit if the same file is read over and over and over again.
I have a question. Is there any configuration the user specifies to define the partition? Like, should the user partition in a certain way the data that flows in the cache?
So like the only thing you configure is the primary thing you configure is the page size, right?
Okay.
And then it will always be aligned as the file. So for example, if you need to read 1.5 meg of the file, you would read basically 1 meg chunk. So you would read 2 megs and cache 2 megs, but you would only process 1/2 of it if you.
Okay.
Yeah. So yeah, it's configurable. Page size defaults to 1 meg, so you can't change it, and it's stored. Each megabyte is stored as a separate file, and the files are bucketed, so each directory is not too large. If you have large directories, you can also have performance issues, and supports high concurrency read. And if worker restarts, Alluxio tries to recover the cache data. So if your worker has a temporary issue that went down and then goes back, it will recover the cache data, so you don't need to read it from read mode again. And it exports various of cache metrics for monitoring. So you can directly monitor the cache performance from Presto. And on the Presto side, how Affinity scheduling work is basically use a hash-based solution. So for example, use consistent hashing to pick 2 workers, and you check whether the first worker is busy or like it's not busy, so basically, is it not busy enough to be able to schedule the split on it? If it works, then you schedule it there. Otherwise, you choose the second option. And if both workers are busy, in this case, Presto will just choose a random worker and not caching the data. So if the preferred worker are busy, we don't pollute the caches on other workers. You can just make sure the data is still processed, but then you don't keep a copy of the data at a random worker, which would never have a cache hit, basically. Yeah, so if it's a dynamic cluster setup, use consistent hashing to avoid data reshuffling. And yeah, because the effective cache size is your cluster's total worker size, or like all the SSDs on all your worker, right? If you want to cache more data, the less copies of a single piece of data you cache, the more data you can cache for the total. So that's kind of like a way to make sure we have a good cache efficiency. So we have some benchmarking data, and these are like comparing, like the caching for, and so for P50, P75, and P95, and you can see that, generally speaking, it's better, especially the tail latency is way better than if you don't cache the data. And so the Presto RaptorX architecture is Presto plus Alluxio local caching, and also include some other caching services that's not for file data cache. For example, it also caches metadata. It's also kind of caches the result for file listing. And like file descriptors, footers, those are specifically for like columnar storage format that, you know, footer has the information of like all the stripes, for example, for org. So those are also cached.
How do you keep, I guess my question is like, how do you keep the different services from stealing each other's resources? So how does Presto not steal resources from Alluxio? And then within Alluxio, how do you reserve resources for caching pages or footers, etc.?
Yeah, so this is a nice thing of like running Alluxio as a library inside Presto, right? So you have only one service, so there's not like two services like competing for resource. And typically what we suggest is leave the memory to Presto because data like query processing is memory intensive and use SSD. So mostly like all the SSDs are managed by Alluxio and then memory are used by Presto.
Okay, neat. And sorry, one more question. How do you end up like pre-caching, like running some queries to tell the cluster, okay, this data is going to be hot, so that you can cache that set of data and query it faster?
Yeah, so there are some follow-up works that we'll talk about later to kind of address that.
Okay.
Yeah. So yeah, so that's kind of like what we end up with developing, and because we had this collaboration, RaptorX, like we started the idea at the beginning of 2019. By the end of 2019, it was actually already in production, and in 2020, it pretty much replaced all the previous Raptor clusters. And while we're replacing the Raptor like clusters workload to RaptorX, we were able to like it's kind of the usage organically growed to like double the size of the previous usage just because, you know, it's easier to use and transparent to users and everything. So, you know, yeah, and then like the performance and everything are still like pretty good compared to previous Raptor implementation, and we don't need to manage a separate storage system anymore. So it's kind of worked out pretty well for both of us. That's why we were like, you know, okay, let's have some follow-up work. One thing that we want to figure out is how to estimate the working size, right? Like I want to allocate SSD. So, you know, I'm setting up my workers. How much SSD should I have on each worker? This is kind of like depending on like how big is your like hot data size. So the challenge here is we need to come up with the online estimation because you know, like nobody can afford running all the workload again for a week, try to figure out what is the size, you know, like, and because it's an online estimation, so while we're serving real queries on like real workload, the estimation itself need to have a low CPU and memory overhead, right? You don't want to affect the production queries. And we want to also support sliding window work set estimation because, you know, the analytical queries are typically the days data or like hours or like weeks. Typically like analyzing for the last month is already pretty rare. So we normally try to target to say like caching the last week's data, how much data, or like caching the data for 1 day, how much data you would need, like that kind of situation. And then it needs to be pretty accurate, right? Like otherwise, you know, you don't want to come up with a random number. So the solution we come up is to use a cuckoo filter based shadow cache. Basically we're trying to track data access as insert. So when you're trying to access a piece of data, we insert a data point into the cuckoo filter, and the clock field will track the latest access. So it's kind of a modified cuckoo filter implementation that also has a clock. So that like if you have a clock and then you kind of periodically aging, for example, like you initialize it to 7 if you want like 7 days, and then every day you kind of decrement it by 1, and when it reaches to 0, that means that day can that data can be deleted. We choose cuckoo filter because it supports delays and it's pretty memory efficient, and it's also fairly easy to implement compared to some of the harder kind of estimation filter implementations. So yeah, so this is kind of how the system works. So when we try to evaluate, basically there's a working set size, and then there's a cache hit ratio that you would so basically once you insert the data that you're supposedly would cache it if you have infinite cache size, and then next time when you access the data, you can track your hit rate, like if you can't cache everything, right? So, and then you can evaluate whether your working set size is larger or smaller, like your hit ratio is larger or smaller in different cases, and you would be like, okay, I have my SSD is too large, I actually don't need this much, or I have enough, or like I have too little. Like if I increase the size, then like I would have a better cache hit ratio. So you can kind of depending on the ratio, you can figure out where you are at. So that's kind of like a way for you to estimate your working set size and configure your cluster with the optimal cache size. And another problem we want is, sometimes I know I don't have enough cache space and I can't get more SSDs, even if I wanted, I don't have the choice. So in this case, instead of trying to estimate how much cache I would need and configure the cluster, I just need to figure out what data I want to cache, right? Then this is the situation that typically in at least in these large internet companies, we already have data on which tables are hot. So you already know from various other sources, from previous tracking and everything, right? You know what is your hot data. But then how do you tell Presto and Alluxio that only cache these data? So this is kind of a configuration based solution that we have right now. So you can basically say for this database and this table, cache these partitions only, or cache these number of partitions. So it will basically cache the latest partitions and phase out the older ones and get the newer ones. So that's kind of a thing.
So it'll cache the most recently created partitions, or it will cache the most recently accessed partitions?
I would it's the accessed. So
okay. Thanks.
Right, so these are kind of the work. Obviously, we have other works planned down the pipeline for further improvement for both actually for this cache filter. If you actually combine those two, right, you can use the shadow cache to estimate what is the hottest data, and then directly just without having to configure it directly, only cache the hot data. If you combine the two features together. So that's something that we're working on for future improvements. Yeah, so now let's see the industry adoptions. So this was in Meta, as I said, since late 2019, 2020, and it's completely replaced the Raptor cluster. The primary usage is A/B testing. The A/B testing framework was the framework that Raptor was designed for. It's basically powered a lot of the product experimentations. If I want to launch a feature, how does this feature compare to the baseline in terms of user engagement or any other metric you want to define? That's a general framework that's widely used by product engineers in Facebook. So we completely replaced that use case with RaptorX. And then the dashboarding is another thing that, if you want to have a faster dashboard load time, typically what people used to do is inject their, dimension tables into Raptor and then query that directly. But now they don't need to do that. Yeah, so that kind of back in the day with Raptor, that was also a kind of a headache, because basically the workflow for a data engineer is, okay, I want to build a dashboard on this data. Okay, directly using Presto is too slow. I want to use RaptorX. And then you need to kind of apply for like getting your data into RaptorX. So you have to set up ingestion. And then like once you have all of that, and then you can use it. And then if you don't have enough storage system, like we don't have enough capacity on Raptor for like your organization, then you kind of out of option, right? So with RaptorX, that's all out of the window. You can just use it, like, you know, we'll cache the hot data and then problem solved. Right, so these are all replaced with RaptorX. And
Rongrong, we do have one question, if I may interrupt, in the chat. If you want to open up the chat,
sure.
it might be easier for you to see it. I'll read it out loud while you read it as well. Andrew Smith says, I don't know too much about this. However, it seems that cloud storage and compute is a large remote version of a local computer. There's the node engine, which represents the CPU, hot data cache. I'm not sure what the arrows mean, Andrew.
Optimized to
Equivalence. Okay.
Okay.
So for those on the,
I feel like this is a very big question. Yeah, I'm like, I don't think there's an answer, or at least I don't also feel like I have an answer for this question, like whether there's a like optimized architecture for the cloud. I think we are all trying, like cloud is still a pretty new thing, right? And so like this is one kind of a solution or one like try on optimizing the data access and everything for the cloud. Is it optimized? I don't know. How do you define what is optimized? Like there probably can be like better solutions, especially because you're mentioning monument like architecture, you know, that's kind of like a classic thing for computer architecture. Like I can't really say that this is the like, you know, enterprise sweeping like whole thing for cloud. But I think they're like a lot of people are trying to attack those problems, and the solutions are kind of converging in a way that you would have the tiered storage, and like so you would have the tier storage as, you know, caching the hottest data like in memory and then on SSD locally, and then, you know, in some like cluster like relay like close, and then, you know, like your really remote cheap storage. That's kind of how where the industry is heading to. Like I don't know whether this is a satisfying enough answer for you. Okay, let's continue. Yeah, so because this was so popular and like it works pretty well, so we also kind of enabled RaptorX, so Alluxio as a local caching layer on the generic interactive analytical workloads for Facebook. So kind of like anybody who would run ad hoc query against the whole like Hive data or like that Meta has, you know, we try to enable caching, like, you know, on those clusters too. So if like kind of repeatedly running analysis on the same data sets over and over again, you would also benefit from caching. And this is also in production in Uber. Uber's kind of production environment is very different from Meta. Meta pretty much, because, you know, we are moving from Raptor to RaptorX. So we came from like, basically the starting point is we have enough cache capacity for all the data, right? Because data used to actually stored on the local. We actually kind of effectively has more caching capacity because the code data, we no longer need to cache them. Instead of on Raptor, we still have to keep the data locally on Worker. So in Meta's workload, a lot of the times the cache hit ratio is like 90+%. Uber has a different situation. They never used RaptorX, so they never used Raptor. So they have very limited caching capacity. Only some of the workers have SSD. So they're really trying to make it more efficient for their cache usage. And that's also where the configuration-based caching setup, cache filters are like a collaboration between engineers at Uber and Alluxio. And they also have the dynamic cluster membership situation where like the cluster size can like grow and shrink. So it's very important to make sure that we use consistent hashing for Affinity scheduling rather than like some other like non-stable caching algorithms. And another challenge for Uber is they use Hudi. So Hudi tables can change very frequently because there's updates. As a result, we also kind of optimize for like you can use not just file path, but use file path and modification time to compute the hashing to make sure, you know, if your table is updated, you don't end up like read an older version of the data. Yeah, so like as you can say that the collaboration between the two open source communities benefits both community. For Presto, it means, you know, we can delegate the caching solutions to caching expert. We don't need to worry about how to manage cache and how to manage local, like small local files and stuff. And it also dramatically speeded up the, like kind of from conception to development to production timeline. We basically finished this whole thing within a year. And it's like running in production within a year. And for Alluxio, as a like file system caching layer solution, it provides Alluxio very good insights on how upper layer storage or like compute engine works and what the users would actually need and what kind of semantics or like features Alluxio should develop to better serve the users, right? And the tighter integration also means we have better performance. And then we can also develop features that's more relevant to the specific engines. And also, like, you know, it's a benefit for the whole community of open source users. So there's also ongoing future collaboration ideas. So first, we also want to be able to persist file metadata caching, and then table level cache metrics. So currently the caching metrics are on files, but you know, for analytical queries, we obviously care more about the table level metrics rather than just file level metrics. And they're like rate limiting on the cache access and like adaptive cache filter based on, like I kind of mentioned that, you know, if we combine the shadow cache and cache filter together, you know, you can have adaptive cache without configuration. We also want to have a semantic aware caching. So this is kind of for specifically for Parquet or for Orc. You know, if we can understand the semantics of the file format, then we can cache data more efficiently and effectively by only caching the columns that's actually needed rather than like caching kind of aligned with the column, but the file segment. And then native cache client and library for, you know, for example, C++, because, you know, C++ is kind of getting popular as query engines. Facebook is doing Velox as a like a C++ engine, like, so it would be nice if we also have like, you know, caching solutions in other languages as well. Yeah, so that's all the talk. Thanks, and for more questions, please speak up. Thanks.
Awesome, thank you. This is fabulous. Folks, feel free to speak up if you want me to unmute you. I can. You can post in the chat. One question that came to my mind: some of our members might not know exactly. You have a file and you have a table. How are they different?
Okay. So this kind of also depends on your table format, what table format you're using, right? But historically, for like the Hive kind, so Iceberg and Hudi are kind of variation on top of the traditional Hive. But basically, Hive formats is kind of like a directory would be a table, and the table would have partitions. So each partition would be actually kind of like a subdirectory, though like if you are storing your data in S3, then it's a bucket. So it's just the prefix, like your prefix is table, and then you have the part of the path that's describing the partition, and then inside the partitions you have files. And then depending on whether your table is bucketed or not, if you have bucketed table, then each bucket will be a file. If it's not a bucketed table, it's just like a table. It's kind of depending on your upstream, like when the table is generated, how many like sources are writing to the file. So in terms of Spark, that will pretty much be like how many drivers that's like, writing files. If it's Presto, it's also kind of like how many Presto workers are writing the file, because each of the source that's writing probably writing a separate files. So one thing to watch out for Presto users specifically is if you have a lot of small files in your partition, your query performance would suffer. So merge your small files into a larger one. Yeah. Any other questions?
That's a good tip. I see there is another question from Andrew. Is this Presto Alluxio integration designed for querying a database for an industrial application? Could I use this for a distributed scientific computing use case where there are very high CPU uses?
So Presto can't, Presto only has a SQL interface. So if you're querying, if your SQL query, then it's probably good to use. Though again, if your data fits in one machine, then I would say like choose a better solution for a single machine architecture. But if you have your data just kind of stored in like a object store with like a metadata like store on top of it, then Presto would be a good solution. Whether Presto Alluxio solution makes more sense is because Alluxio only speeds up the data read, right? So the larger the portion of the time your query is spending on reading data and more repetition you're reading the same data, the more speed up you will see. So depending on like if it's a compute intensive and you're only reading the data once and will never read it again, I would say Alluxio is probably not going to help on much. But if you're repeatedly reading the same data, even if it's a CPU intensive, you will still have some speed up. But again, it's only speeding up the IO part of your query. So depending on the percentage.
Okay, Andrew says, understood, thank you. And Silu wonders, is this handling data with updates?
So traditional Hive format doesn't really support updates, but like newer format like Hudi would support upserts. So it's not really the same as updates. So you basically can add more data. I guess this is kind of like what it is. So if you're using Hudi, we support Hudi and we support Iceberg. So if you're using these formats, it would work. Performance-wise, it would obviously suffer because whenever you update your old data kind of are invalid, you need to read data again and then cache the new data. But so it works.
Does that happen automatically in this case where you're using Presto and Alluxio, or does it happen on the next time the data is queried?
So when you're processing your, so when we receive the query, we'll do parsing, analyzing, and then we'll ask Metastore, what is this table and what are the data, right? And then Metastore will give us the latest data and we'll use that for query. And if that data is a newer version than the data we already cached, then the already cached data is useless. We still need to read from the remote storage. So if you're like kind of files are updated very frequently, and every time you're processing a new query, it ends up to be a new data, then like your cache is not very useful at that point.
Got it. Makes sense. Sounds like it's about finding the right use case.
Yeah, yeah. Like no solution is a one size fit all.
Right. Yeah. Makes sense. And maybe we'll open it up for any other questions. Feel free to ask. At this moment, I'll take the chance to thank Rongrong and our sponsor AI Camp because they're a great partner. And this has been a great talk. Rongrong, would it be okay if people contact you like on LinkedIn to ask questions? Or
Yeah. Sure,
great.
sure. Feel free to contact me on LinkedIn.
And
Like,
if they want to try out
outside.
this architecture, who should they reach out on a Slack channel?
Good point.
Alluxio may have a
You
community
can
Slack.
look, yeah. So like either asking the Alluxio, I think asking the Alluxio community Slack would you would definitely reach us, and we'll give you pointers. There's actually blogs talking about how do you try this. So if you just Google and search, and there's already like blogging examples to show how to like set it up. And then if you have any questions or any issues while using it, you can always reach us in the Alluxio community Slack channel.
Great. And Chen posted that in our chat here. Fabulous. Thank you, thank you, thank you. I think it looks like you've answered all the questions. So I think I learned a lot, especially as part of the discussion. So thank you so much for doing an interactive talk.
Thanks a lot for hosting us.
For sure. Yeah, and this will be recorded and we'll share the link.
Thank you. Okay.
Thank you. Take care.
Bye.